for the data design, we have chosen my design data set. And first I have imported the data set to the Google Colab, and here going by the structure, we had 58 classes, and the classes were imbalanced as well. So therefore, before begin, we have to create train, validation, and test folders. In here, I have used 70% for test train and 15% for both validation and testing. Here you can see the classes. For the data pre-processing part, we have cleaned the data using check for corrupt images, and we have found 0. In the augmentation part, we have do the training, validation, and testing data. And here finally we had this amount of data to train and this amount of data to validation and test, total samples. And these are the some random samples from our image data set. So first I have built a custom CNN model to do the classification part. First I have import 22 for beach extraction part and export into detail for reduced spatial dimensions. And likewise, I have trained the model within 20 epochs. It only got accuracy of 77 and validation accuracy over 90. But at the finally, we had for the testing part, we had accuracy of 88% and precision score of 0.88. And that was my part.
Part of our deep learning project on traffic sign recognition, I am covering MobileNet V2 on one of our 4 supervised models for classifying signs from a Kaggle dataset. It's efficient, perfect for real-time apps like autonomous vehicles. MobileNet V2, proposed by Google in 2018, uses depth-wise separable convolutions, inverted residuals, and linear bottlenecks to cut computational costs while keeping accuracy high. It was about 2.3 million parameters, far fewer than ResNet 50, 24 million, making it ideal for mobile devices. We use transfer learning with a pre-trained ImageNet-based freezing layers and adding a custom head, global average pooling, a 1 to 8 unit dense layer with ReLU, and a softmax outpooling for 58 classes. Pre-processing including resizing to 224 by 224, normalization to 0.1, and augmentation with rotation, flip zoom via Keras image data generator to handle our imbalance 3,375 image dataset. Training and use Adam Optimizer 0.001 categorical cross entropy, batch size 32, and early stopping over 20 epochs. Test accuracy 96.15 on 675 images. Precision and recall hit 1.0 for many classes, but rare ones varied due to imbalance. Compared to our custom CNN, it's faster and more accurate. ResNet 50 beat it at 99.56, but MobileNet V2 excels in speed, accuracy, balance for edge development. In short, MobileNet V2 shows efficient model can deliver strong results for practical DL transportation. Thank you.
VGG16 model is the one of the most widely used deep convolution neural network for image classification. For our project, we selected VGG16 because it has shown excellent transfer learning capabilities on real-world image datasets, and we want to explore how it performs on traffic sign classification. Instead of training from scratch, we used transfer learning with a pre-trained VGG16 weight from ImageNet, which already contain millions of general image features. We frozen the convolution-based layers. This means those layers were used purely for feature extraction, and we already feature extraction, and we only trained the top layers that we added ourselves. Our custom classification had included a pattern layer, a dense layer with 256 neurons using rule activation, a dropped-out layer of 0.5 to prevent overfitting, and finally a softmax layer with 58 output neurons presenting each traffic sign classes. We trained the module using the Adam optimizer with a learning rate of 0.0001 for about 25 epochs, applying early stopping for prevent overfitting. The results were outstanding. The model achieved about 97% validation accuracy and 96.9 test accuracy with smoothened training curves and minimal loss oscillation. The confusion metric shows that VGG16 correctly classified most categories, although it occasionally misclassified visual similar signs such as speed limit of 30 and speed limit of 50. Compared to our custom CN baseline, VGG16 improved accuracy by almost 9%, demonstrating the power of pre-trained deep architectures. The main limitation was a training time. Due to 15 million parameters, it required a strong GPU and took longer to converge. However, in return, VGG16 provides very stable performance, excellent generation, and a reliable benchmark for the rest of our models. This model effectively proved that the transfer learning is the key factor in achieving high accuracy with limited data. And here are the results of the VGG16, the accuracy, precision, and the recall and the F1 score of the VG16 models, and the comparing other three models. Thank you.
Of this project, I was responsible for building and improving the ResNet 50 model. Then, as you heard, ResNet 50 is very powerful and pre-trained model. This code shows how we started. We loaded the model pre-trained on ImageNet, but we set trainable false. So to freeze all its layers. So I actually implement on two different versions of ResNet 50, and the difference between them is a key reason for our success. The first version was our starting point. We froze all layers, only trained the new layer we added on top. So you can see here we added our own classify on top, but because the base was frozen, the model struggled to adapt. The results were okay, but not great. The validation is accuracy was only around 33% after 20 epochs. So we created second updated version. This time we made crucial changes. We unfrozen the last 4 layers for fine tuning. This technique called fine tuning also the model to adjust its most complex features to better recognize traffic signs. We also made other smart adjustments. This is the first one. Second, we used lower, more careful learning rate for fine tuning. So this is third, we added learn rate scheduler that automatically reduce the rate if the model stop improving. So this is the early stopping code. The results were dramatic. The updated ResNet 50 accuracy shot up of our 99 percentage.